Neuro-Symbolic AI. So I am a psychologist, and I did my thesis in cognitive science, and I modeled a car driver, and I wrote several thousand rules to model a car driver driving in traffic. And when I wrote my thesis, I already, in my thesis, lamented the fact that machine learning wasn't there yet, and I couldn't do, say, object recognition, right, in a simulated world to help with my model, right? So I'm really happy to see now that in recent times everything came together, right? And now I can use both logic and machine learning for almost anything I want to do. So in 2021, I started writing about neuro-symbolic AI, right? Or what we call composite AI, where you use various types of AI to make your inferences better. And in 2023, it was picked up by Gartner. I mean, I was not the only one writing about it, but there's Gartner kind of picked it up. So it's on the hype cycle. So now we know it's really real, right? Um, and and Gartner also kind of talks about why they think it's so important, right? Um, and and we would say that the most important drivers for neuro-symbolic AI is trusting your data. And I talked about it when I started, but let me say it again, right? LLMs hallucinate. Machine learning models have biases or not always give you the right response. And logic is also not always the answer, right? So, but if you can get these three types of AI to work together, right, you might trust your data more. And also, if you use these three types of AI systems together, your data might also get way more explainable, right? So you might be in a hospital situation, and you have a beautiful machine learning model, a recurrent neural network, or a convolutional model that does fantastic prediction, but you just don't know why, right? Well, an LLM could look at that particular patient for which you have a prediction and explain to you why this might be the case, right? Anyway, so that is trust and explainability are the main parts, of course. And then, of course, you always want to have the semantics, right? I mean, if you live in a machine learning world only, right? And I mean classical machine learning, not the new LLM stuff, right? Again, you can't really talk about anything. You need semantics to make things to get real entities that you can talk about. So let me stick to that one here for now, right? And so we make this claim that AllegroGraph is a neuro-symbolic knowledge graph. But what do we mean by that? Well, let me explain. So when our knowledge graph industry started working, right, and we started about this 15 years ago, we already were 100% symbolic, right? So we had ontologies and taxonomies, and we used description logics. And then we at AllegroGraph also have a fully functional compliant Prolog compiler built in. So we also can do constraint-based reasoning, multi-step planning, what-if scenarios, things you really can't do with the machine learning model, and something that LLMs are not yet ready for, right? So this is very cool stuff, and now let me take a step back, right? So this is the symbolic stuff that we've been doing for a very long time, right? And then for the last 10 years, right, almost any knowledge graph that we built had a machine learning component, whether it was for airplane maintenance or predicting customer choices or predicting diseases, right? We all had it, used machine learning for that. We did graph neural networks, we did recurrent neural networks, we did classification of entities, anomaly detection, right? And linked it very closely to our knowledge graph. And then recently, right, in the last 2 years, we had this amazing explosion of AI, right, using LLMs and vector stores, right, where we now can use entity and event extraction on the local and structured content in our knowledge graph. We can do query answering on both local and remote knowledge. We can do any kind of symbolic reasoning, prediction, explanation, causal chains, etc. Right? So we have this knowledge graph and we have all these technologies around it. So let's go a little bit deeper into, okay, the strengths and the weaknesses of each of these three systems, right? So, and I won't go too deep here, but I mean, so first let's look at logic, right? Or the symbolic logic. I mean, if you can use rules, right? The rules can be extremely precise and they're very deterministic and consistent. So I mean, it's if you can do something with a rule-based system, I always say, please do that, right? Because and it's the most consistent thing you can get. But the problem is, and I don't know if anyone in the audience had done it themselves, but if you write a system with 2,000 rules, like I did for my driver, and then you add rule 2001, well, that one rule has so many opportunities to interact with all the other rules, right? That before you know it, then you're debugging for hours and days, right? To add this one more rule to your system. So, and then of course, the world is always changing. And every time you want to deal with a novel case, you have to write more rules and it gets more and more complex. So that is, so the strength is it's precise, consistent, transparent, and explainable, but it's really hard to maintain and complex. Then machine learning. I mean, when we started working with machine learning, it was almost like magic, right? You give it the right feature sets and it will learn and adapt from your data without writing any rules. And it can apply to a very large data set and learn all kinds of patterns that you might be interested in. But on the other hand, and we've seen this as a real problem in several domains, we have the black box problem. We just don't know why the machine learning uh, took a particular made a particular choice, right? And then there's always the data quality and the quantity um, issue, right? I mean, garbage in, garbage out, and uh, and then there's the ethical issues, right? So I'm actually from the Netherlands, and about 4 years ago, the Dutch government had to, 3 years ago, the Dutch government had to resign because they were using a machine learning model at the Dutch IRS to figure out whether or not certain people might be cheating on their child care funding. And that machine learning model was chock full of biases against ethnic minorities, right? And so basically, anyway, you get my point there. So this is for machine learning. And then we have, of course, LLMs with their strengths and weaknesses. I mean, it's amazing in what it can do with natural language understanding. I never thought as a psychologist that we could get to this particular point, right? But there's always these hallucinations. I never, ever trust anything that comes out of an LLM, right? I always have to double or triple check, right? So this is the strengths and weaknesses. And I'm sure almost anyone in the audience knows about this. So people started writing about how can these systems make each other better, right? And we found this beautiful article in Science Direct, right, where someone describes really well how you can have a symbolic knowledge graph with knowledge. You use the symbolic knowledge graph to create embeddings. So now you can change your, well, you can add it to your machine learning models. The machine learning models will start learning and it will learn new patterns, new rules. You can extract those from the machine learning models. There's a lot of new software that can help you with that. And now I changed my symbolic knowledge graph and then I can maybe make new embeddings, right? So this is a beautiful picture of how people try to have these systems make each other better. But this is only symbolic knowledge graphs and neural. I was kind of tempted to put in one more thing here because what I found is that you can even ask an LLM to create a feature vector. So if you ask an LLM, hey, what are the features I need for a machine learning model to predict whether or not someone is going to get, say, a disease like GERD, and right? It will both create a feature vector for you based on the content in the knowledge graph and the Python program to run it, right? So another example of how these systems can make each other better. And so we in AllegroGraph, right, created this framework, right, where we can talk to the LLM, and I showed you that in great detail. And in the past, And you know we can do the symbolic reasoning, right? Because that's what knowledge graphs do. And then we have the machine learning frameworks that we can talk directly to from our knowledge graph. For example, if you anyway, we can do neural networks, take the output, feed neural networks directly from the knowledge graph. So we have these systems. And so if we, for example, apply this to healthcare, right? Then, and I'm going to talk about this in way more detail, but say I have a healthcare knowledge graph with patient information and taxonomies and all that, right? I can start learning based on all the events for all the patients using recurrent neural networks and then use that to predict future events. But I can also predict future events by taking a sequence of medications, diseases, procedures, observations, tests, feed it to an LLM, and based on the fact that it read 36 million PubMed articles, it will also come up with a prediction, right? And of course, I can do this in symbolic information. I'm going to talk about it in a minute, right? So the example I'm going to talk about, I've talked about this before, and I'm not so much interested in talk about healthcare today. This healthcare knowledge graph that we have is one of the best playgrounds, right, to take all these technologies and see how you can mix and match them all together. So for years, we worked with a hospital in the Bronx, where we had 3 million patients in a knowledge graph using an entity event knowledge graph model. This is an article that came out in 2022, where we describe the benefits of this particular event modeling system. And this was a great model, but the problem was that we couldn't show this to anyone because it had patient data in it. So what we did is we took the patient data out and filled it in with or synthetic data that was created by MITRE. It's called Cynthia, or we inserted Mimic, which is anonymized data in this knowledge graph. And now we can give this to hospitals, right, to play with our knowledge graph and about 10 Jupyter notebooks with any kind of analytics you can think of, right? So you can practice working with knowledge graph to see if you really like this particular thing, right? So anyway, I actually provided DALL-E in my ChatGPT with an abstract of this paper, right? And said, can you make a visualization of this? And it came up with this beautiful visualization. And so I'm keeping this one, although I also have a more psychedelic version, which most people like even more, but I think this one looks a slightly more business-like, right? So anyway, I'm kind of really enamored what I got out of DALL-E for here. Okay, so now let's talk about my healthcare example, right? In terms of this neuro-symbolic AI healthcare. So let's begin with how can I, for example, diagnose or prescribe or report or predict using symbolic reasoning, right? So I'm going to show you in a minute, but we can, let me take a step back. So we have this disease called GERD, right? About 20% of people in the United States have this problem, what they call gastroesophageal, I can't pronounce it, reflux disease. I call it GERD, right? And here is a simple logic program in Prolog, right, where we can predict what someone's risk level is for this particular kind of disease, right? And we might have some facts that the patient is obese and smokes and has frequent heartburn, blah, blah. And then we could say the risk level of GERD for this particular patient is high if the patient is obese and the person or smokes or has hiatal hernia, and he has or frequent heartburn or regurgitation and eats large meals, right? Well, then your risk level is pretty high, right? So this is using a symbolic system to predict whether or not you might get GERD, right? And this reflects also in some way how doctors actually think about it. I can also use a neural network, right? I can take in my knowledge graph all the people that get GERD, take all the events that led up to this, and then take a control group of patients that look demographically like these patients but did not get GERD, right? And then train a recurrent neural network, and then we can predict whether or not someone is going to get this particular disease, GERD, right? Or I can take a sequence of events for a particular patient and then give it to the LLM, and then based on the medical history of this patient, right? I can also a prediction. I don't want to go too deep in there because otherwise it would take way too much time, right? So all these three things can predict GERD, right? Now, how can these systems make each other better, right? So I'm just going to go through this fairly quickly, but an LLM can explain the machine learning outcomes, verify predictions from the verify the predictions, or do even feature engineering, right? And an LLM, right, can also make the logic system better, right? So it can ask for more facts before committing to a prediction. But actually, the logic that I just showed you, this logic, was written by an LLM, right? So I asked, and this took only a little while, and it wrote a full functioning Prolog program, right, directly from the LLM. Now, where am I here? I'm here, right? So it wrote actually a logic program for me that then doctors can apply directly. And then how can a symbolic system help an LLM, right? Well, or work with it? Well, I can ask the LLM for diagnostic help, but I can also feed the LLM with the medical history. Then a symbolic system can create the feature factors and the event sequences from machine learning. And a neural network can, say, for example, test the efficiency of clinical care plans. I mean, this is endless, right? I just try to give you a few examples of what you can do, but I hope this makes sense to you guys, right? So a few seconds, let me just make this slightly more understandable for you guys. And let me talk about this thing that we call patient graph again, right? So this knowledge graph that we started with the hospital, and then where we took out this the actual patient data and put in the simulated data, right? Or the anonymized data. So in this system, we have 350,000 clinical trials from the FDA website. We have about 100,000 PubMed articles, mostly COVID related. We have the adverse effect, the effects of vaccines, and we have electronic medical records from Cynthia or from a data set we call Mimic 4, which is anonymized data, right? And at the heart of this is UMLS, right? So you might have heard of UMLS, but it's all the taxonomies in healthcare. They include we have about 180, but here are the biggest ones. ICD-10 are the billing codes, the procedure codes, and then we have, for example, the terms for clinical drugs, et cetera, right? And then everything harmonized with what we call the meta thesaurus. So this is the UMLS. And then because 80% of all the medical data in our knowledge graph is unstructured, I mean, you couldn't do really very intelligent queries. So we had to use an LLM. In this case, it was BioBird, right, to extract all the medical terms from PubMed and from the clinical trials and from the electronic medical records and the and this database, right, and harmonize it. And that means that we now have this model where, say, this is a patient. This is the medical record of one patient. So this patient had an encounter. Could have 1,000 encounters, but one encounter with a condition, acute viral pharyngitis, right, which links to an ICD-10 code, acute pharyngitis, which then links to UMLS into SNOMED or the meta thesaurus, right? So here you have the taxonomy tree for pharyngitis, right? But we also have clinical trials. So here's 2 clinical trials that both talk about acute pharyngitis, right? Here's the short summary of these clinical trials. And we have PubMed literature, so 2 articles from PubMed, again, talk about sore throat, which relates to pharyngitis. And then we have the FARS database that, again, talks about sore throat, and which is related to pharyngitis, right? So within one knowledge graph, we have linked all these data sets together. But the really cool part is here, right? So talking about neuro-symbolic AI, you think, so how does it all come together in the knowledge graph? Well, here is how it comes together, right? We have what I call the symbolic reality, right? You have a patient, that's the demographics, and encounters, like this encounter has sinusitis, this person, right? So here is the symbolic reality. But we have a process, a pipeline, where I can take the sequences of events for, say, this particular person and all the people in the database, right? Train an RNN, and now I can actually predict whether this person is going to have GERD, right? So here's a prediction. So this is an event, just like this event here, but in this case, the event comes from an RNN, and it's 0.286 certainty that we'll get this. There's more information here also about the time frame when you think you're going to get it. And here we see that the LLM looked at the sequence of events and also came up with a prediction that this person is going to get GERD, but it also gave us a reason why this might happen, right? And it's a little bit more certain than the machine learning model that this is going to happen. Now, once you have this, right, so I hope you understand how the knowledge graph ties everything together, right? So you have the symbolic logic, right? You have the LLM and RNN, but where it comes together is that you store the output of these various systems in the same knowledge graph, because that gives you then a handle to do other things like find the cases where the LLM and the RNN both predict the same breathing plugs for the same patient, right? And you could click here and then you would find, but you can also find when they not are the same, right? And yeah, again, I wish I was in an audience where you guys could ask questions. That would be better, but I hope you get the point, right? So how a knowledge graph literally ties all of this together into one system. And that was literally all I wanted to do for today. So thank you for your attention.